Let me start with the main challenge, which is sharing my screen. Here we go. Let's see. Please let me know when you can see my slides and I'm ready to go. All right. So welcome to this session where we will go out and meet the social side for architecture. And the reason I would like to do this talk is because we, as a software industry, we often talk about the importance of teamwork, the power of team autonomy, and that kind of stuff. But I have seen that it's notoriously hard to get those things right. And when we fail, we tend to fail miserably. So in this session, I would like to approach software development from the people side, the side of social psychology. And you might, of course, ask yourself, why do I feel qualified to talk about psychology? I'm a programmer, right? I am. But I also happen to have a degree in psychology, which is one of my big interests. And I've written 2 books about this intersection of technology and psychology. The first one was Your Code is a Crime Scene. And then I have my more up-to-date book, Software Design X-Rays, that came out just a couple of years ago. And I would like to start this talk by showing one of the things that really surprised me when I started to study psychology. And this is actually a controversy. So let's see where this takes us. Did you know that within psychology, one of the best psychological measures we have is a personality measure? It's something called Big Five that can measure your personality. So what you do, you take a test like that, and you might have done something similar as part of a job hiring process or an evaluation, something like that, right? So you basically answer a bunch of questions and you get a score on how extroverted versus introverted you are, how open you are to new experiences, and things like that. And it's a high quality test. The question in psychology is, of course, if I knew each of your personality scores, could I predict how you would behave? There was one group of psychologists that claimed that, yes, of course, that's what personality tests do, right? To tell us how people will behave. But then there's another group of psychologists who claim that, no, not really, right? Even if I know what personality score won't help, because the situation is way too complex, right? And situational factors will dominate. And the first time I heard this, I was like, wow, this is something I've seen before. This is Emacs versus Vim, right? This is Git versus Mercurial. This is static versus dynamic typing. So, it's almost like a tendency towards controversies and strong opinions. It's almost like it's a human thing. Who knew? And of course, like most controversies, the reality turns out to be somewhere in the middle. And there's this quote here from our study that claims that, in fact, 91% of differences in people's behavior cannot be accounted to by personality tests. So what this means, in other terms, is that a personality is important because it kind of predisposes you to act in a specific way. But the way you will actually act depends on the situation. And the reason I tell you this is because this has influenced how I view software architectures. Because to me, a software system has a personality and situational forces too. More specifically, I like to view the software architecture as a system's personality. Right? An architecture is important because it predisposes what we can do with the code base, which features we can easily add, which stuff that's going to be hard. But the most important thing, just like when it comes to predicting human behavior, are the situational forces. Because I would like to claim that no matter what the code looks like, no matter what the architecture looks like, if we get the right people together with the right technical skills, the right domain skills, we could actually succeed no matter what architecture we have, right? It might not be the most efficient, but we might succeed. However, if we get the situational side wrong, the people and organization, then no matter how clean our architecture is, we will never, ever be able to build a successful system. And this balance between personality and situation in a system is something I've experienced firsthand several times. So let me share a story with you. Let me tell you a story of how perfectly readable code can become unreadable. So this is something that happened to me maybe 10 years ago in my previous life as a software consultant. So what happened here was that it was a company, and that company, they were actually in a fairly good position because they were going to build a new version of an existing product. So they had some very accurate historical data that kind of showed them that, using our 5 in-house developers, we will be able to deliver this thing in just 1 year. Now, you think that the software project, that's predictable. That sounds odd. And of course, it didn't take long from someone from marketing to come down and say, 1 year, that's not good enough. We need to have this in 3 months because we have this really important trade show where we have to demonstrate it. It's a must. So how do you take something that will take you 1 year to build and compress it down to just 3 months? It's fairly easy. It's simple math, isn't it? Just throw 4 times as many developers on it. And they did. So they actually hired 25 software consultants and threw them on the project. And the main problem here was that the initial architecture was already set. So as you can imagine, this project didn't really deliver in 3 months. In fact, they didn't deliver in 1 year either. It took them 2 years to deliver. And the reason they managed to deliver at all was because they had to cut the scope and they had to deliver with a number of known defects. So to me, this doesn't really sound like a good deal. They could have done this with 5 people in 1 year. Now it took 25 people 2 years. And what surprised me here was that I wasn't part of the project initially. I came in later for, I like to call it like the post-mortem, right? And what was so interesting was that when I talked to developers, all of them kind of claimed that this code is virtually impossible to understand. It's a true mess. It's the worst kind of technical debt you have ever seen. I was a little bit surprised to hear that because I've been analyzing their code. I have been reviewing it. And I mean, it wasn't like it was a work of art, but it was perfectly fine code, and it was definitely not hard to understand. So why this perception? Well, the reason was, of course, because if you have 25 people work on the same parts of the code all the time, and your architecture can kind of support that many people, what's going to happen is that you're going to have a really, really hard time maintaining a mental model of the code. So let me try to clarify this. When we as developers or software architects, when we reason about source code, we almost never have a perfect copy of the code in our head. What we have instead is an imperfect mental model, right? We have a mental model of what the code looks like. And when you have that situation where you have way too many people, when you have an overstaffed project, what happens is that your mental model, even if you write a piece of code yourself today, then you pick it up 3 days later, it's going to look completely different because 5 other people have been working on it in the meantime. So your mental model gets outdated really, really quickly. And I find it so fascinating that when we talk about readable code and maintainable code, that goes way beyond any technical properties of the source code. And social factors will influence how we perceive a code base. Now, this project I'm talking about that was supposed to take 1 year and now took twice as long and became much more expensive, that shouldn't come as a surprise to anyone who has read The Mythical Man-Month. It's one of my favorite books. It's an old book, but I still find that so many parts of it are highly relevant. So if you haven't checked it out, please put it on our wish list. It's a really good book. And The Mythical Man-Month is best known for what we now call Brooks' Law, where Brooks claimed that adding resources to a late software project makes it even later. And Brooks even has a formula that explains why this happens. And I have visualized it in a graph, so let's have a look at that. So what you have in this graph is, on the y-axis, you have the number of months until completion. How long does it take you to deliver this particular thing? And on the x-axis, you have the number of people you're adding to the project, right? And what Brooks shows you is basically that to a certain degree, you can add more people to a project and you get a quicker completion date. That's natural. You can parallelize some tasks and get more work done in a shorter calendar time. But what you also see is that there seems to be some kind of turning point, right? And beyond that point, the completion date drifts further and further away. So the reason this happened is due to the increase in coordination. Because if you think about it, the number of hours you have available, they increase linearly with the number of people you add to the project. But the potential coordination paths increase almost exponentially, right? So the trick for any project is, of course, to detect when do we reach this turning point? When is our architecture saturated with developers? And overstaffing is a very common problem. And there are a number of other risks. It's not just coordination risks, but we also run other risks with overstaffing. And these two tend to be softer aspects, motivational factors. And just to give you an example on one such motivational factor, there's this concept of social loafing from psychology. And social loafing is a type of motivation loss, and it's something that occurs when we feel that the success of our team depends very little on our own actual effort. So what we tend to do in those situations is that we sit down and pretend to do our part of the work, but in reality, we really just try to look busy and hope that our peers keep up the effort. And it sounds like a horrible, horrible thing, right? But it's a very human thing. And social loafing tends to happen when the goals of a particular product or project aren't clearly communicated. Or a sure way to introduce social loafing is also to introduce arbitrary deadlines. That's when people lose motivation really, really quick. And it simply becomes harder in a large project to see how my individual contributions can make a difference, which will impact my motivation. Even I, as a developer, I'm a human after all, right? So why do we keep repeating the same mistakes? The Mythical Man Month is a 45-year-old book, and still projects and companies fall into this trap this very day. I think the main reason is visible here. So if you look at this piece of code, by looking at this code, we just cannot tell, is this function, which is part of a much larger module, is this module a coordination bottleneck for our 5 different feature teams? Or is all that code written by a single individual that keeps all of that information in their head so that we have a key personnel dependency? Who can tell? Well, from source code, we just cannot tell. And this is something I like to call the great tragedy of software design. That the organization that builds the system, we're invisible in the code itself. And I think this is very unfortunate because what tends to happen is that we tend to attend to symptoms rather than the real issues. And I have listed some of the common symptoms that I tend to see in different organizations. So we might have things like, as developers, we complain about the complicated merge conflicts between the different branches and development features. And we might even run the risk of unexpected feature interactions, which is some of the worst bugs we can ever have. And we might have code that's hard to understand. We might have branches that live for weeks, right? And I'd like to claim that if you see any of those symptoms, it's very, very likely that the root cause is situational. It's not necessarily a technical issue, right? It's most likely an organizational, social issue. So what I would like to do now is to show you how can we bring visibility of the organization into the code. Well, the starting point here would be to see, can we detect parts of the code where people from multiple different teams have to coordinate their work so that we have a potential coordination bottleneck. And what I'm going to use to measure this is something called Fractal Figures. You see an example here. The way you do this is typically done on an architectural level, right? So you define your architectural building blocks, which might be a service or layer or component, whatever. And then you consider that as a square, right? And then you measure how much has each team contributed to that code over a specific time period. And you use a unique color to visualize each team. So what you see here in the example is that given a specific component, Team 1 has written 51% of that code, but we also see that Team 2 and Team 3 have done considerable contributions, right? So this seems to be some kind of collective effort here. Now, this is the visualization, and I'm going to give you some more specific examples soon. But to really reason about large-scale systems, we need to have a way of actually measuring this, right? So what I use is a formula from a research paper quoted on the bottom that can take a fractal figure and normalize it into the range 0 to 1. And I'm not going to walk you through the math. All you basically need to know is that we take some numbers, how much has each team contributed, and we end up with a number between 0 and 1. And I've tried to visualize how that works. So we see that if we have a component and all of the code is written by just one team, then we have very, very low coordination as seen from the code, virtually none. So we have a fractal value of 0. And we see that the more fragmented the development work becomes, the closer we get to 1, right? So this is the metric we're going to use. But the question is, of course, where do we get the data? How do we know if a particular team have worked on a piece of code or not? Well, the good news are that this is data that you all already have. We're just not used to think about it that way. I'm talking about a version control system. And you see a simple example from Git here. Because the fascinating thing with version control is that it's actually social data. Our version control system knows exactly which developer that wrote which piece of code and when they did it. So this is data that we can take, and we can take individuals and we can kind of just aggregate them into our teams. Because these metrics tend to be most interesting on a team level. The main drawback I see with version control data is that it's very file-centric. Whereas when we talk software architecture, so we want to kind of raise the abstraction bar and reason about the architectural building blocks. So what I tend to do is I typically take the contributions to the different files, and then I group them into my logical architectural building blocks. And I simply aggregate all contributions to all files that match a particular pattern in my file system. And then I put a label on it. And you can basically use any grouping mechanism that you like, as long as the resulting building blocks, as long as they carry some kind of meaning in your architectural context. And I'm going to show you some examples on how to do this on layered architectures and how to do it in microservices. And by doing this aggregation, we can finally start to reason about the social side of our code. So let's start to do that and look at some real-world systems. And let's do that so that we can identify some common social ways to fail with software architecture. And then we're going to look at what we can do instead to mitigate those issues. All right, so I would like to start with a true classic, layered architectures. So I would assume that most of you have seen this picture before, or at least variations on it, because this is a true classic. This is the modern view controller pattern, right? And it's still very popular to this very day. The only thing is that this is never, ever what a modern view controller implementation looks like. Because we all know that we need to have a services layer, right? It's vital. And then, of course, we don't want to write the SQL by hand. So let's encapsulate that behind an object relational mapper. And we also need to have a repository layer on top of that, of course. And the reason we need a repository layer is something I have to admit that I've been thinking about for 10 years now, and I still haven't come up with a good answer. So let's just kind of duck the discussion by calling it the best practice, should we? And of course, this is not where it ends, because we need a data abstraction layer as well, of course. And the reason we need a data abstraction layer is that otherwise I don't get to use all those cool mock features from my unit test framework. And then, of course, it sounds like we need a business layer as well, right? Because after all, we're doing our business application. And then we might have view models and so on. So it's not uncommon to see layered architectures with maybe 9, 10, 11 different layers. Now, the interesting thing here is, let's do a thought experiment. Let's say we have the architecture to the right. And let's say we want to do a simple tweak to the user interface. We need to just add a checkbox. How will that simple change impact our architecture? Well, I actually have some data on that. So this is what's going to happen. That simple change is going to cross-cut through all layers and require modifications to every single one of them before it ends up in the database. And the numbers I have measured is that in a layered architecture, somewhere between 30 to up to 70% of all commits, all changes that we do, will require modifications to all layers. And the lower number, 30%, that's for stable applications that are more in traditional maintenance phase, right? Where most of the work tends to be minor bug fixes that often are local. Whereas the higher number, 70%, that's for systems that are under active feature development. So to me, this kind of sounds a little bit expensive, right? In 70% of all cases, I have to modify multiple architectural building blocks. That doesn't sound like a proper encapsulation. And the reason for this change coupling, as I call it, kind of manifest the consequences. They manifest themselves when we take the team perspective. So let's apply our fractal value and fractal figures to a layered architecture. And the example you see here, if you look to the right, that's a visualization of, it's a real software architecture. It's a commercial system that I'm allowed to use as long as I keep the data anonymous. But I try to find kind of similar names on the different building blocks. And the way you read that visualization to the right is that each one of those circles represents an architectural component. So we see at the top, we have something called an administration controller, then we have administration views, presentation models, presentation views, and so on. And the color simply indicates the fractal value. Remember, 0 meaning no coordination between teams. Closer we get to 1, the higher the potential coordination between teams. And you see they're all glowing red. And we see an example here from the administration view that it's indeed a shared effort between 5 different teams. So this is what it typically looks like the moment you put multiple teams on a layered architecture. And it's also the reason for one of the most frequent questions that I get. Should we use component teams or feature teams? We kind of tried both and none of them really seems to work. The reason none of them seems to work is that with component teams, you typically get a clear separation of responsibilities, which is good in general. The problem in a layered architecture is that that's going to lead you to very long lead times. Because each one of the layers, the APIs between them, they kind of tend to become a coordination bottleneck in themselves. So we need to do handovers, we need to synchronize, we need to coordinate. So with component teams, you tend to get quite long lead times. Now, if you switch to a feature team, things tend to be even worse because suddenly your whole architecture is a major coordination bottleneck. Because now you might have multiple teams working the same parts of the code, but for different reasons, since they work on different features. So which one should I choose? I don't think we can answer that question in isolation, because we cannot fix what is fundamentally an architectural issue by purely organizational changes. They always need to go together hand in hand. And to me, moving from any form of organization, let's say component teams, to something else, like possibly feature teams, is ill-advised unless we also consider what the architecture supports. We don't want to work against our software architecture. And this is something that I've seen many organizations experience, and also think this is one of the reasons behind the recent hype and popularity of microservices. Because if we travel in time, maybe go back in time 5 or 6 years to the rise of microservices, what tended to happen back then was that microservices were often sold as a promise to deliver certain capabilities. The most common one was that by adopting microservices, we can get a system that's loosely coupled, right, with independent parts. And by having independent parts, we can finally get that team autonomy with very low team coupling, right? We can simply assign one team for each microservice, and the teams can work more isolated, right? You can minimize the coordination overhead. And as a consequence of that, we get all these good things. We can suddenly scale services independently, right? We can spin up more if we want to load balance them. And we can deploy services independently. So each service can kind of have its own lifetime, which again facilitates team autonomy. Wonderful. Is this what the real world looks like? Let's have a look at some examples. The first one is again from our real world system. It's an organization that moved away from a monolithic application to a microservice architecture. And then we measured the team coordination. How does it look in that architecture? And this is what we found. Surprisingly, it looks almost identical to what we saw earlier with layers. Most of those services tend to be coordination bottlenecks. How come? Well, I think you can see the reason. If you look closely here, you can see the names of each one of the services. So here we have something called translation server or diagnostic server, right? And access control server. And if you look at those services, you see that those names, they tend to kind of represent technical responsibilities. So what we have here is not so much services as a bunch of distributed technical components. And that means that if you want to implement if you want to implement a specific feature, you typically have to touch multiple services. And as a result of that, you get a very high team coupling, a high team coordination, because the architecture is simply technically oriented, and that misaligns with the work of the team. And the work of the team always tends to be feature-driven or use case-oriented. So there's a mismatch between the work we do and what the architecture supports, even though they had a microservice architecture. So as a consequence of that, we definitely didn't get any loose coupling. Everything depends on everything. As a consequence, we simply cannot get any real team autonomy, and we can definitely not realize the benefits of independent deploys because all of it belongs together. It's a ball of mud. So it's easy to think that this was a failure due to lack of modularity, because you couldn't see that in the visualizations, but each one of those circles representing a service, they were actually quite big. So their services were like 20,000, 30,000 lines of code, which is anything but micro, right? So maybe if we manage to introduce small and truly modular services, maybe that will solve the problem. Well, I'm going to show you an example on that. But before I do that, I'd like to take a step back and talk a little bit about software complexity. When we as developers talk about complex code, what we're often referring to is code like this, right? Lots of conditional logic, really, really hard to follow the overall flow, hard to change, hard to understand. But there's a different kind of complexity as well. And that is when you have small modular parts that each one might be simple and easy enough to understand in isolation, but the emerging system behavior is anything but simple due to the tight interdependencies between the different components. So in the second case, the complexity is still there, only now it's distributed. So to truly reason about microservice architectures, we would need a way to uncover the interdependencies between them. So let me show you the approach I'm typically using to uncover dependencies in microservice architectures. I use a concept called change coupling. I have a blog on it referenced in the bottom right corner, and I have several chapters on it in Software Design X-Rays. And the way change coupling works is that it's very different from the traditional coupling that we talk about. When we as developers or architects talk about coupling, what we are typically referring to is a dependency, right? We have a piece of code here, it uses some code over here, they depend upon each other. But change coupling is different because change coupling is about human behavior. So it's something we can only measure from the evolution of our code, from Git data. So here's an example. So let's say we have a simple system with just 3 different services. And the first time we make a change to that system, we're modifying the subscription service and the sign-up service together. The next time we make a modifications, maybe to implement a new feature or fix a bug, we modify something else. The third time we do a change, we're back to modifying the subscription service and the sign-up service together. So if this is a pattern that continues, that those 2 services are always modified together, then we know that there is some kind of logical dependency between the subscription service and the sign-up service because they kind of co-evolve like this. And this change coupling metric is something we can use to visualize and reason about microservices and the cost of change. So what I'm going to do now is that I'm going to show you a change coupling analysis of our real-world microservice system. Here's what it looks like. And the way you read this visualization is that each one of the microservices is a node in this graph, right? So each one of these labels represents a specific microservice. And the lines between them, they simply show the change coupling dependencies. And in this first example, we see that we're modifying a service called estimated conversions. And when we change that one, we have a predictable modification in 7 other services. Wow, that looks like quite some tight logical dependencies here. And just to show you that this isn't a fluke, here's an example from another service. This is estimated profit. Change that one, and 5 other services go with it. Now, change coupling, the reason I talk about it is because it's tightly coupled to the whole aspect of organizations and teams and architecture. And what we can do now is we can take the same system that I showed the change coupling before, and we can visualize it using the fractal values again. So as on the previous visualizations, each one of those circles that you see represent a specific microservice. And the color shows the fractal value, right? And again, we see that there's some very, very high coordination needs as seen from the code between different teams. We have 5 teams, 4 teams, 3 teams working on each one of those services all the time. And this is even though, again, you cannot see that in the visualization, but you see that the circles are smaller. So now each one of the services, they were really, really small, like 500, 1,000, 2,000 lines of code maximum, right? So small, easy to understand services. So why does this still happen? Why do we get this change coupling bomb? Why do we get this inter-team coordination nightmare? Again, I think the answer to that is within the names of those services. So if we look at just some of the names here, we have something like subscription costs, payment accepted, payment received, and so on. And while I would like to claim that those names, they sound like they could be good properties, maybe even objects, but they do not work particularly well as service boundaries. So I like to claim what we have here is not so much microservices as distributed objects. And the consequence is that the only way you operate upon this architecture, if you want to add a new feature, is via shotgun surgery. And it's very likely to involve tight coordination with multiple different teams. So even though we had these small, highly modular services, we ended up having a very tightly coupled architecture. And as a consequence of that, we simply couldn't assign some kind of ownership to different teams. Everyone had to work in the same part of the code. And as a result of that, there was absolutely no way that any service could be deployed independently. You change one of them, and you typically had a whole cluster of services that need to go together. And this is something you simply cannot fix it by enforcing an ownership, because the fundamental problem is the architectural building blocks. So this is the kind of architecture that will transform your weekly calendar into a chessboard of simple planning meetings. And of course, at this point, some of you are most likely thinking that, yeah, but what I have been showing so far isn't really microservices. It's more like microservices. And you're correct, of course. But that's not my point. My point is that microservices is a high discipline architecture, and they're incredibly hard to get right. And when you design a microservice architecture, you're also doing social design. And if you forget that, then all is lost. So what should we do instead? Well, let's have a look at some examples from organizations that have successfully addressed this. And I like to start with the perspective of Conway's law, right? Because Conway's law has a tight impact on modularity. But modularity alone doesn't really guarantee a successful architecture that facilitates parallel work by multiple different teams. We saw several examples on that, right? Instead, what I have found is that our architectural boundaries, they have to align with the responsibilities of our teams. And to me, the only successful way I've seen this done is that by aligning our architectural building blocks with concepts from the problem domain. If we manage to do that, then we manage to create natural boundaries for the teams. So in an architecture, if I look at the names of the different services, what I would like to see are concepts with a problem domain. That tends to be when you can parallelize work and create interdependent building blocks. So can we do that in microservices? Of course. People are doing it. I've seen organizations be very successful with microservices. But what I really want to point out is that microservices alone is not a guarantee for loosely coupled architectures. In fact, it might even be harder to have a loosely coupled architecture in microservices. So in particular, microservices won't cure any of our dependency blues. If we want look to create loosely coupled architectures, a microservice isn't a solution, right? We should have other reasons to choose microservices, because microservices are an expensive and high discipline architecture. The organizations I've seen that successfully implement the microservices and operate them, they tended to follow a number of principles. One is that they tended to have fairly small microservices. They definitely were in size, but they tend to have microservices partitioned by business capabilities, not data, like we saw in the previous example, right, with the change coupling bond. So microservices partitioned around business capabilities means less coordination overhead. And it also means that you can typically have quite a small team. And with a small team, I mean maybe 3, maximum 4 persons. Because I think beyond that, you open up for the risk of social loathing and those other motivational factors. And it simply becomes so much easier to coordinate with 3-4 people. You don't even need a process for that, right? So I think there are a lot of advantages by keeping microservices team-sized. But of course, not all of us are doing microservices. So let's have a look at some alternatives to layered architectures in more traditional monolithic applications. There are several approaches. The one I have seen work successful in several different contexts is something called package by component. It's an architectural pattern, and there's a very good write-up by Simon Brown that I reference here in my slides. And the basic idea here is that instead of partitioning things in layers, which is a technical partitioning that doesn't have anything at all to do with the problem domain, the thing we're trying to implement, what we do instead is that we look at the problem domain and see what business capabilities do we have. And then we encapsulate each one of those business capabilities in a component. And if you do this, then again, you might be able to create fairly good partitionings for the different teams, because now you can assign a team to each one of the business capabilities and they can become the domain experts in that area. What I have seen with package by component is that even though you tend to minimize the amount of coordination needs in the application code, there still tends to be one coordination bottleneck. And that is the database. You know, the black hole of maintenance efforts. And it's easy to create coupling in the database, right? So even if the business capabilities, the application code are independent, they still end up being logically coupled via shared data in the database or shared queries. So this is a fairly hard problem to solve. And basically we have to make a decision. We have to prioritize. And if we say that a property like autonomous teams and low coupling and coordination between teams, if that's important to us, we need to do a trade-off. And the trade-off typically involves taking some logic out of the database. So things that the database could normally do for us, like searching and sorting, we might have to take that and pull it up to application code, right? It's always a trade-off. But by doing that, and with some high discipline, I have seen organizations be very, very successful with monolithic applications. I have to point out as well that package by component, one of the reasons I like that abstraction is because it kind of gives us a very consistent architecture in the sense that everything is a component. It's easy to reason about. It's easy to navigate. But at the same time, it enables diversity in the actual design of each one of those components. So let me explain what I mean by that. Let's look at the component to the left here. So maybe this business capability is a little bit more complex. So maybe it will benefit from some additional structure. So maybe we could even do an internal layered architecture here. And then we have another business capability, B, which could be very, very simple. maybe we don't even need the database. And if that's the case, we could even implement the whole feature in a single file. So we can have different local implementation styles depending on what the problem actually requires. And this is a major shift away from traditional layered architectures, because in a layered architecture is a one size fits none, right? Whereas here, technical decisions are now local decisions. And that's what I really, really like about this architectural style. So to sum it up, if we express natural team boundaries in architecture, then we get a lot of advantages, right? And modular boundaries are always based on concept from the problem domain rather than the solution domain, because that's where you get the natural ownership. I'm going to talk a little bit more, but before I do that, maybe you're interested in giving this a try on your own code, your own systems. So what kind of tools do I use to do this analysis? Well, first of all, it's truly fascinating how far you can get with a simple command line and a Git client. So here's one of my favorites. I have lots of examples on this in software design X-rays, but here's one of my favorites. If we do a Git short log with the -s flag, then we can point Git to a specific folder that might specify a component or a service, and we get the sum of all the different contributors. So this is the data that we can aggregate into teams, and we can then calculate the fractal value on that. What I use myself is a tool that I've been working on for 5 years. It's called CodeSyn. Some of you might have heard about it or seen it. But CodeSyn kind of does all the heavy lifting with Git and supports the higher level operations like architecture, analysis, and teams. And if you're interested in this, then please consider to support CodeSyn. You can look it up at codesyn.com. There's a free version of CodeSyn as well. So, with the tooling covered, I'm going to give you some additional links at the end. I'd like to wrap it up by claiming that Conway's law that I mentioned earlier is actually an oversimplification. Because Conway's law is basically the idea that we want to have an alignment between our architecture and our organization, right? But I would like to claim that if we take Conway's law to the extreme, let's say we create a truly successful architecture from a team autonomy perspective, where each team has a very clear boundary where they can do all the work with a minimum of coordination to other teams. If we take that into extreme, that isolation, what we tend to do is we tend to run into other problems. And those other problems, they are social in their nature. More specifically, we tend to put ourselves at risk for what psychologists call the fundamental attribution error. And the fundamental attribution error is actually quite common. It's something that happens to us all the time. And the fundamental attribution error means that we attribute the same observable behavior to different factors depending on whether it concerns our group, my team, or another team. And just to give you an example, right? Let's say that you work in a large organization, and let's say that you get to work and the nightly build has failed, right? And you know that it was your team that broke the nightly build. Yes, I know, it's a highly hypothetical situation, right? But let's go with me for the sake of the example. So when that happens, you know that the reason you broke that nightly build was because you were under a tremendous amount of stress, right? You were really trying to do your best to support the business and meet this impossible deadline. And it was a very tricky change in some really nasty legacy code, right? And besides, that nightly build has never been that stable anyway. So you see, a lot of situational factors, right? Things that don't really have anything to do with you, but the situation and context. Whereas you know for sure that if my team breaks the nightly build, then you know it's because we're a bunch of lousy, careless cowboy hackers, right? And that's our personality. So more specifically, this is the core of the fundamental attribution error, that we tend to overestimate personality factors when we explain the actions of others. And this is a really, really dangerous thing. And as you've seen in the presentation, I kind of like to visualize things. So I tried to find a visualization of the fundamental attribution error. And this is the best thing I came up with. I think that captures the core of this social bias. So what this means is that the fundamental attribution error can wreak havoc on any organization. It can completely destroy any software endeavor. So what we need to do is we need to kind of bridge the gap between the different teams, while at the same time minimizing their coordination overhead. This really sounds like a contradiction. I mean, how can we have an isolated team and at the same time having them work together? But it's only a contradiction because we fail to distinguish between what I call operational boundaries and knowledge boundaries. So what do I mean with this? Well, what I mean with this is that a team's operational boundaries, the parts of the code where we do most of the work, should be kept quite narrow and aligned with problem domain concepts like we talked about earlier. Whereas on knowledge boundaries, the parts of the system that we are familiar with, where we know a bit about the code, we understand a bit of the domain, and more importantly, we know the people on those teams. Our knowledge boundaries should be much wider and should typically include all the systems that we need to interact with so that we can counter things like the fundamental attribution error. And this is not something that's just going to happen. This is something we need to design into the very organization. And I have seen this done using a number of techniques. A very simple thing is to just make it a habit. If you do something like code reviews or pull request review, make it a habit to always invite people from other teams to your reviews. Not only might that bring you an important different perspective, it also helps you to get to know the people on other teams as persons, which again is something that reduces the risk for fundamental attribution errors. Another thing that I've seen successful is to encourage people to rotate teams. I wouldn't enforce it, but if some developer is more interested in a different part of the domain, then let them work there. Everyone will benefit, right? Finally, I've also seen in large organizations, I've seen them adopt an open source inspired ownership model where each team kind of owns a particular service, but anyone can make changes to it. And if you do that, so that basically means you can reduce potential bottlenecks. So let's say my team is really busy with some planned features, and you need to do a small change to our API. You can do that change yourself. You can submit a pull request to us. And if you do that work well enough, then the team will accept your pull request. So it kind of removes that coordination bottleneck. And if you have wide enough knowledge boundaries, it's actually a viable model. So, with that said, I'd like to sum up by claiming that there is really no such thing as a good or bad architecture in isolation. And I have this quote here where I say that, you know, the ultimate test to me of an architecture success is if we can implement a new feature without calling a grand staff meeting. That's when we know that we have succeeded. And an architecture to me is good when it supports the changes we want to do with the system. And then architecture never ever exists in a technical vacuum. As we have seen, the social side of our code will impact many important aspects of our software architecture and our system. And I hope to show you today and inspire you to actually start to measure and reason about the social side of code based on actual data from how the system evolves. And before I go over and have a Q&A session, I'd like to point you to some additional resources in case you want to read more on this. This is still a fairly young field. I have several chapters on it in Software Design X-Rays, in case you're interested in that. I also have some interactive examples at codesyn.io, so there are some analyses of well-known open source projects, so you can start to explore things like fractal figures and fractal values and visualizations and get familiar with the concept. I blog about this regularly at codesyn.com and my private blog at Tornhill.com. And now, before I go over and take questions, I'd like to take this opportunity and say thanks a lot for listening to me. I hope you enjoyed the session, and may the code be with you. Thank you.
Ja. Okay. Halløjsa. Tusind tak, Adam, for et rigtig spændende oplæg. Min maskine crashede så fuldstændig nu her, så jeg er lige lidt i panik ved at få den startet op. Det beklager jeg selvfølgelig mange gange. Men fedt Adam, og jeg synes, det bekræfter til fulde min egen erfaring som arkitekt derude. Det er ikke de tekniske problemer, som er de egentlig vanskelige. Det er den sociale side af det, den organisatoriske side af det. Og hvis jeg lige skulle hive fat i en anden tidligere keynote speaker fra SAOS-konferencerne her, Søren Larsen fra IT-universitetet i København, der har analyseret postmortem også 35 offentlige IT-projekter, som er kørt helt i hegnet. Så siger han, der er ikke nogen af dem, der er døde på tekniske problemer. Det har været organisatorisk, det har været projektstyringsmæssigt, det har været alt muligt andet end selve teknikken. Det er altså ikke der, det driller. Godt. Vi prøver at lave en Q&A-session nu her. Jeg prøver lige at indtage talerstolen og skifte over til Gather Town, forhåbentlig. Ja, er der nogle spørgsmål til Adam? I kan prøve at række hånden op, der er sådan nede i bunden af skærmen derinde midt på, hvor der også er settings og den slags. Der er sådan en hånd, den kan I prøve at smide i vejret, så kan man stille et spørgsmål.
Jesper, vil du sige noget? Okay, Jesper gik ned og satte sig igen. Ja. Godt. Jeg ved ikke, at der ikke er nogen spørgsmål.
I hope you could hear everything well and that the sound came across clear. And did that work well?
To me, it was fine. But I was into the Hangout, so yeah.
Yeah, it got better. It was a bit. The first.
Yeah, I'm really
minutes.
Curious as well to hear your reflections because I know that on bunch of different systems as well. So
yeah.
Did anything of that I told you, did it resonate with your experience or?
Okay, we have Jan Larsen. You have raised your hand. I'll put the spotlight on you. So hopefully you'll be able to talk to everybody. Go ahead, Jan.
Yeah, can you hear me?
Yes.
Okay. I'm sorry, I don't have a question. I just wanted to tell you that you still have an echo when you talk, Jakob.
Okay.
Maybe you have two microphones or something?
I might.
Oh, do you still have YouTube open? Just mute YouTube. Maybe that's the echo.
Det bliver meget værre nu.
Okay. We are working on it.
Der er ikke noget ekko hos mig.
Okay. Og det er ikke fordi din YouTube er åben, Jan. Så får du den 2 gange nemlig.
Jeg har lukket vinduet i hvert fald.
Okay. Ja, det er jeg. Jeg tror ikke, vi har ikke nogen devices i rummet her med optager. Okay. Er det bedre nu, Jan?
Ja, det er faktisk.
Super. Så prøver vi at fikse det. Okay. Men ellers, Jan, nu du har fokus, var din lyd OK fra på Adams oplæg?
I begyndelsen var der en del udfald, men det blev bedre. Så alt i alt var det OK.
Okay, det er godt. Tak. Andre, der har nogen, som har nogen spørgsmål, så fjerner jeg lige dig fra Spotlight. Ja, Martin, du har Spotlight nu.
Thank you. It's maybe a little bit too specific a question for Adam, but because we use CodeScene today, this measuring team coordination needs. Is there a way to exclude, an easy way, I should say, to exclude boring commits? So like, for instance, if we're upgrading all of our Docker base images in services, that maybe we just have one guy in one team doing that for all services, but that would maybe show up as a coordination need, which I don't really think it is. Team coordination.
Yes, of course. You might have things like cross-cutting concerns and stuff like that, which is well under control. So, yeah, it's a very specific question, but you can actually exclude any content that you want from the analysis. And it's something I often do. So if you have some infrastructure code that's truly shared, then I typically don't include it in the analysis because it might become misleading. Or you might even introduce a specific architectural component that captures that cross-cutting concern around the different services. So you can always get in touch offline, and I can provide some more specific examples and screenshots on how I do that.
Great.
I hope I managed to answer the question.
Great. Thank you. And Peter, you have a question as well. You're on the spotlight now.
Thank you. Can you hear me?
Yes, I can.
Okay. So this is, in my organization, we are a large organization. We recently started, a couple of years ago, with the journey from project-based to team-based, agile techniques, microservice, all that. And we have been told that stable teams is the way to go. So we try to keep the members of the teams stable. Of course, people are leaving the company sometimes, and newer ones are getting on. But you mentioned at some point that you think we should rotate the members of the teams. Could you elaborate a little bit on that?
Yeah, sure. I can do that. So I also think that having stability in the teams is important, because I remember being in organizations myself where the teams changed like every second month, and it's very frustrating for everyone. So I think having some kind of stability in the core, I think that's important. But at the same time, I also think you want a natural flow of people between the different teams. I think some developers naturally want to learn more about the system, so they would like to work on different parts of the code base. And I don't think you should enforce it, because it's never a good way when it comes to knowledge work to kind of force people to do things. But I think you should encourage it. If I, as a developer, would like to work on different part of the system as part of a different team, it should be very easy for me to do that transition. By doing that, you get a number of advantages. First of all, I can take everything I learned about this part of the domain with me to the other part, which can help us build a better system as a company. Because if you have truly static teams that don't change for years, what can easily happen is that you get silos instead. And you might actually see that there are some very good practices that kind of one team does, but don't naturally spread to another part of the organization. And you can kind of try to do that with a bunch of different techniques. You can have regular seminars and stuff like that, but I still think nothing really replaces the spread of domain expertise. And the only way to get real expertise is to work with something. So that's why I'm a big fan of that pattern. Did I manage to clarify?
Yes, that clarifies a bit. So we should do it based on the needs of the developers, and not as much based on the needs of the sort of the organization also. But because developers want to change a bit or try something new.
Yes, some developers want. Other developers are very content to work on the same part. But I do think it's a big win for the organization too, because you spread the domain knowledge, right?
Yep.
And I think that's the big win. So it's motivating for people, and it's also a win for the organization as a whole. And it helps kind of glue teams together, because it's so much easier to code, particularly in these times of remote work. So all of us are probably doing remote work now, right? But I do think, and I've been running a remote team for 4 years. Right? And the reason that has been working so well is because we have gotten to know each other as persons. So even if we're 100% remote, we make sure that we meet a couple of times a year. And I think there's nothing that can replace that, right? And it's the same thing with even if you sit in the same building, you can still have complete silos. And to actually know someone as a person on another team, I think it's really, really important because we humans, we are social creatures.
Great. Thank you, Peter.
Just one.
And Sultan, I'll put the spotlight on you. Here you go. And you're muted, Sultan, I think. Sultan, you're on now, and I think you should unmute your mic. On you. Here you go.
Hello, can you hear me right now?
Yes, I can. You're muted, Sultan, I think.
I tried to make it work, but I don't know.
Sultan, you're on now, and I think you should unmute your mic.
I did it.
Just by YouTube. Sultan, I think you're on YouTube rather than GatherTown. Could that be?
Oh, my question went away.
I am muted, but it's something fishy, so I can't talk to you guys.
Sultan, I think you're on YouTube rather than GatherTown. Could that be?
I try to do that.
All right. All right. Any other questions for Adam? It doesn't seem so. Adam, a big virtual applause to you and your talk. I think it was excellent. Jesper, do you have a question? We'll just take one more question. Jesper Wermuth, here you go.
Yeah. Am I on?
Yes, you are.
Okay, cool. Thanks for a nice talk, Adam. It's very interesting with the analysis parts. I was thinking that this could be kind of hard to implement if you have a running system because the required changes, they go all the way through the architecture. So do you have what kind of experiences do you have introducing this pattern in an existing architecture as opposed to greenfield?
Yeah, and I think I've seen it successful several times. I've been part of the team doing that work as well a couple of times, and it is of course challenging. I first like to point out that even if you do a greenfield project, then I actually think this kind of stuff is even more important to get right from the beginning. And I do think we need to measure. I think we need to bring that level of visibility to it because it's so easy to start to couple different things and create coordination nightmare. But when doing this with an existing system, what I typically do is I do it iteratively and I do it with very hard priorities. So it's not like you do a big bang migration, of course. What you tend to do instead is that you tend to try to identify the natural components that might be smeared out across different layers today. And a powerful way of doing that is by using the change coupling analysis that I showed you today in the presentation. So I talked about change coupling on an architecture level where you have different services that kind of change together. But you can easily do a change coupling analysis on a file level. And that kind of shows you what are my actual modular boundaries inside on a specific architecture. So I do a change coupling analysis, and then I typically use the business priorities, or I do what I call hotspot analysis. Basically look at where has most development activity been over the past year. And I start with those parts. And the change coupling analysis will show me that if I pull out this particular feature, then this file from the database will follow along, the following files from the service sets, this code over here that's shared. So I simply start to extract it component by component. And what I also find is that even in a large legacy code base, let's say you have a layered architecture, a lot of that code tends to be stable. Oh, I got muted. Did I talk too much?
No, it's perfectly okay. You got muted for some reason. I don't know why.
Yeah. What I wanted to say is simply that you don't have to take it all the way, right? So you can often have the existing legacy code. It can typically run in parallel for a very, very long time, right? The important thing is that active parts of the code, the ones that you're actually working on extending with new features, you gradually and iteratively migrate them out to a new pattern. So change coupling has been a wonderful way of kind of getting a starting point. So unless you have tried it, I really recommend giving it a shot.
Okay. And a more technical question, does it the code scene tool, does it allow analysis across different repositories, or do you need a single code base?
Yes, it does. It does. It was actually one of the hardest things to implement. And the way we do it is because, to do a change coupling analysis, the most fundamental way you do it is by saying that things are coupled if the change is part of the same commit. And if you have different Git repositories, then by definition, you're going to have different commits. So what we do instead is that we look for things like references to a shared Jira ticket, things like that.
Can you repeat? You look for what commit messages, kind of string comparison style thing?
Exactly. So you need to have the data somewhere. So a simple way of doing that is that each time you do a commit message, then always include a reference to a Jira ticket or a thread or whatever issue track you're using. Because if you do that, then you can simply relate that, okay, the changes in this repo and the changes in this repo, they reference the same issue, the same ticket. So we know they're related. So that's how you uncover that.
Okay, thank you. I'm happy.
All right, great. Thank you, Jesper. Jan, you have another question. Please go ahead. I'll put the spotlight on you. So go ahead, Jan.
Yes, thank you. You mentioned that the database was a bottleneck, and I was just wondering if that couldn't be solved by having a data service team. They would have to know more about certain things than most other teams, but couldn't that alleviate the problem to a certain degree?
So to a certain degree, yes. I think the main problem, I'm speculating a bit now because I haven't seen that implemented that way. But what will most likely happen is that data service team, they will become the bottleneck.
They will become what?
They will become the bottleneck. Yeah. So now that my team wants to implement something, we kind of need to coordinate with them, and they are busy supporting some other teams. So I think it's important that we as a team are able to kind of pull our features through all the way. And I still think, it's doable even with a shared database, but it definitely requires a high discipline because it's so easy that you write a query that kind of couples your data to something in a different table that belongs to a different feature. But with discipline and clear patterns, I've seen it done successfully.
Yeah, okay.
And, sometimes it requires doing those kind of trade-off. Like we might have to duplicate some data, for example. We might have to duplicate some logic. But to me, duplication is less of a problem than type coupling between teams. So I hope I managed to clarify.
Mm-hmm.
Great.
Yeah.
Thank you, Jan, and thank you, Adam, for your answer. All right. Further questions? I don't think so. All right. So, Adam, thank you.
Practical, we can all go out in the real world on our projects with our clients and see all of these things in the work, how they actually affect our projects, and when things go wrong, it's almost always for some kind of social or organizational reason, in my opinion. So I really like to have to get a better background understanding of that. So thank you very much, and thanks to all of you. Jeg skifter lige til dansk. Tak til resten af jer for at være med. Det var super fedt. Dem af jer, der har lyst, der kan vi bare fortsætte ude i fællesområdet uden for biografsalen her. Så lige om lidt, så smutter jeg derud i hvert fald, og så er I velkomne til, og så giver jeg sgu øl derude, så skal I bare joine. Og vi sender et evalueringsskema ud. Vi vil meget gerne vide, hvad jeres oplevelse var med det her. Feedback er utrolig velkommen, og ting, der ikke fungerede, det vil meget gerne rette op på. Så brug lige 3 minutter på at udfylde det her evalueringsskema og submit det til os. Så tager vi de ting til os og gør noget ved det. Ellers får I mere af samme skuffe, og så kommer vi jo aldrig videre, vel? Men jeg synes, det har været fedt at lege med jer med det her, og jeg beklager de få tekniske problemer, der har været. Nok mest mig og min computer. Og jeg håber at se jer en anden gang i det her, så stay tuned, og så hører I fra os. Og som sagt, jeg er ude i lobbyen fra nu af, og I kan bare komme ud og joine.